you have kids, you likely worry about them having cell phones. These wireless devices that we use to stay connected started growing in functionality as I was growing up. My parents worried about me when it came to these devices, of course, but they really didn't have to. My first memory using a smartphone is borrowing my mom's iPhone to read Taylor Swift lyrics. And my second memory is borrowing the phone again to read the details of the phone's latest software update, just for fun. I was 12. My fascination with computers, including the small ones that live in our pockets, wasn't a childhood fluke. So I went to college to study electrical engineering. One of my favorite classes there taught about microcontrollers, which are small computer devices. I watched enchanted as the ones and zeros moved around in these devices. And as my classes went on, I also became interested in how those ones and zeros move between devices called communications, or just comms. Cell phones communicate using wireless comms. For this, you need at least two antennas, a transmitting and a receiving antenna, to transfer information using radio waves. When transmitted radio waves reach a receiving antenna, data is transferred. Every antenna has what's called a radiation pattern, which is like a heat map of how radio waves interact with the antenna. These patterns are the invisible backbone of the wireless devices that now shape our lives. As I was finishing up college, I hadn't yet learned about wireless comms, but I wanted to. Thankfully, my knowledge of communications and computers was key to securing me a job at NASA's Glenn Research Center. When I started, I was handed a microcontroller along with an assignment that launched me into the wonderful world of antennas. I was tasked with controlling something I had never heard of before: phased array antennas. To help you understand phased array antennas, we'll start with the satellite dish antenna, like the cable TV dish on your neighbor's roof. This is what the radiation pattern of a dish looks like. This pattern has one main beam, which is where the majority of the communication ability is focused. If you wanted to point that main beam away from the center and towards another antenna, you would have to physically move the whole dish antenna. But this is not the only type of comms antenna. This is a patch antenna, which is found inside your cell phone. It's kind of like a metal sticker that lets you connect to the internet. You'll notice that the beam of this antenna is very broad. This is ideal for cell phones because you want to stay connected no matter how you hold your phone. But if you wanted to use the patch antenna to talk to something in the sky, things get a bit more complicated. Bear with me here. If you were to put multiple patch antennas together in a grid, the pattern from all of those antennas working together starts to look more like the dish antenna's beam. Each of those small patch antennas now serve as one element in this new cohesive antenna array. Each element is fed by a wave. The peaks of each wave tell us the phase of that wave. And when the peaks of these waves leave the elements at different times, they are no longer in phase with each other, and something interesting happens. You are able to point that main beam away from the center without physically moving the antenna. This pointing technique is what makes these antennas unique and is why they are called phased array antennas. That microcontroller that I was given tells those phased array elements what phase to have in order to steer the antenna's beam. Compared to the satellite dish, phased array antennas can be thinner, lighter weight, and can steer quicker, making them perfect for something that's moving fast, like a satellite, or a drone. Drones are being used for more than just photography. Larger drones are being used for disaster relief, scientific research, and package delivery. They are also being looked at for passenger transportation, as Rocco discussed earlier. Drones need to stay connected to their operators throughout their flight. If a drone can only be controlled from an antenna on the ground, it can only go where it can see that antenna's beam. But if we want drones to go farther, we need that drone to be capable of talking with satellites. While this is traditionally done with a satellite dish mounted on the drone, you all now know that there is another way: phased array antennas. Before I joined the team, NASA Glen's materials and communications groups combined their researching power to design better antennas for drones. For this antenna project, our materials group made a special, flexible version of a material called an aerogel. If you could dehydrate a cube of Jell-O while maintaining its shape, you would have something not too dissimilar to an aerogel. This multifunctional, foam-like material is mostly air, it weighs very little, and radio waves treat it like it's not even there. These properties make it the perfect material to use to make antennas. Once upon a time, phased arrays needed large electronics behind each element to make the antenna work. But for this project, our communications group was able to take advantage of the emerging 5G commercial market. They used small, affordable electronic parts new to development to design a low-profile phased array. The result of this research effort was a thin, lightweight phased array antenna that could curve along the shape of the aircraft. It was a huge success. New phased array efforts at NASA Glen started popping up around this time, which exposed the need for a new engineer to focus on programming the antenna controllers. That's where I came in. As I was programming that microcontroller, I was also learning from my fellow researchers how to understand and measure our phased array antennas. Like the ones and zeros on our computers, antennas are hidden but vital parts of our modern technology, and I wanted to know more. As we were building up our latest research antennas, I was building up the skills to get involved with bigger parts of our projects, like flight tests. 2 phased array antenna projects supported by my controller had successful flight tests last fall. One of these tests was for the second generation of that aerogel drone antenna. This new antenna was mounted on a piloted airplane, which was used instead of a drone for testing purposes. After many late nights and a whole lot of blue painter's tape, chosen to match the color of the aircraft, this antenna flew over Maryland. It was able to communicate with a satellite during flight, proving this antenna design a success. The other flight test aimed to prove a concept for lunar communications. This concept could one day involve using our phased array antennas on lunar vehicles and satellites orbiting the moon. Now, we don't have any spare satellites to test our antennas on, so we headed to South Dakota. But unlike 12-year-old Sarah, I was not there for vacation. We were there to place our phased array antennas on a weather balloon to act as a satellite, and we tossed 2 other antenna systems into pickup trucks to act as lunar vehicles. One truck had a dish antenna. This truck had to stay parked during operation in order to physically point the antenna's beam at the balloon. The other truck had a phased array antenna, and this truck was really able to push highway speed limits while maintaining communications with the balloon's antennas. I told you, phased arrays are great for fast-moving vehicles. During the weather balloon's flight, the engineers in the 2 lunar vehicles were able to video call each other through their connection to the satellite, proving this concept a success. And throughout this test, I was in the ground control room, watching with both apprehension and pride as my controller and its antennas flew at 90,000 feet above the Earth. Our goal with these successes is to guide and encourage the budding phased array industry by proving that this technology can work for new uses and new applications. NASA Glenn collaborates on phased array research with commercial, university, and other government entities to contribute to the growth of this industry. We are actively working with the US Navy to test our next aerogel antennas on cargo drones. Less room wasted on antennas means more room for vital food and supplies. Or maybe one day, your weekly groceries. We are also currently collaborating with Cesium Astro to design phased array antennas to go on real lunar vehicles. Someday soon, we hope we can video call our astronaut buddies from Earth while they go for a joyride on the moon. I'm proud to be a part of the phased array antenna research that we do at NASA's Glenn Research Center. This work will improve the ways that we stay connected while we live our daily lives, zoom through the sky, and travel to the moon and beyond. Thank you.